Hello everyone, I hope you're staying safe and healthy. Welcome to our last lecture for this semester on ME 2010. We will be looking at the concept of moment of inertia in today's lecture. I'll go over the ideas fairly briefly. I will have more in-depth analysis of these concepts in the lecture notes that I'll post on Carmen. And then my aim is to get to a couple of problems by the end of today's lecture. Okay, in the previous lecture we had looked at the idea of centroids. Okay, so previous lecture we looked at the concept of centroids. Okay, and for today's lecture the aim is to look at the concept of moment of inertia. Okay, so the aim for today's lecture is to look at moment of inertia. Okay, we will not be doing too much of the theory behind it, so I'll be posting lecture notes on the theory behind many of these ideas, but we will be mostly focusing on getting the basic concepts out, and then we will be solving problems. Okay, so I just want to make a quick note here by saying that the detailed notes will be posted on Carmen. Okay, our aim is to go through the concepts quickly and solve some problems. Okay, so our aim is to go over the concept from a peripheral point of view and then look at some problems. Okay, problems. That is the best way to understand this particular concept. Okay, so first of all, we will very quickly define what is meant by moment of inertia, and then we will have certain mathematical definitions for this, and then we will get used to what is called as the parallel axis theorem, and then we will start solving some problems. Okay, so first we will define moment of inertia. Okay, so define moment of inertia. All right, and the basic idea is the following. Moment of inertia is a measure of the distribution of a composite section or a shape's area about a certain axis of interest. Okay, so moment of inertia about a certain axis is defined as so moment of inertia about an axis is a measure of the distribution of area of that shape about that axis. Okay, and which implies that moment of inertia is a geometric quantity. So this is a geometric parameter, geometric property of a body, of a shape. Okay, let me write this properly. You can define moment of inertia for areas. You can define moment of inertia for masses. If you define it with respect to an area, it's called an area moment of inertia. Typically, when you go to dynamics, you will also define a quantity which is the same as this in spirit, and the philosophy is slightly different. It's called as a mass moment of inertia. Okay, so this is a geometric property of a shape or a mass. Okay, so our aim in statics is to look at the area moment of inertia. So we shall look at the area moment of inertia, and the area moment of inertia is also called as the second moment of area. Okay, this is also called the second moment of area. Okay, so these are the two things. So we shall be looking at the area moment of inertia, and the other name for this is also called as the second moment of area, depending on the type of people that you will meet. One will call it as the area moment of inertia, some of them will call it as the second moment of area. All right, so this is the basic idea. This is a geometric property, okay, in a sense. Then what we're going to say is, okay, we're going to look at a mathematical definition. We're going to take this as a matter of fact. We will not be proving it. Okay, so the next step is to look at the mathematical definition. Okay, so mathematical definition. Definition of area moment of inertia. Okay, we will take this as a matter of fact. Okay, we will not be proving it. Okay, will not be proving this. Okay, and to define the mathematical idea of moment of inertia, I just take let's say a coordinate from x and y. Okay, so let's say that here is the x-axis, and here is the y-axis. Okay, so this is the y-axis for me. Then let's say that this is the x-axis, and on this I have some arbitrary shape. Okay, so this is some kind of an arbitrary body. Okay, some arbitrary area A. Okay, and what I'm going to say is, okay, let's consider an elemental area in this arbitrary area. The total area of this is capital A, so let me consider an elemental area. This is of course a closed section. Okay, this is not open in any situation, so I'm just going to consider an elemental area, which I'm going to call as dA. Okay, this is going to be called as dA, and let's say that this elemental area, so this is an elemental or an infinitesimal area. Okay, this dA, let's say, is this is almost like equivalent to a point now, and let's say that this is at a distance of let's say y from the x-axis and x from the y-axis. So here are the distances. I'm going to mark them here. Okay, so this distance I'm sorry is given to me as little x, and then let's say that this distance here is given to me as little y. Okay, then the moment of inertia of this arbitrary area about the x-axis is defined as the following. Okay, so moment of inertia of the arbitrary area about the x-axis is written as Ix in this case. Okay, and then let's say that the moment of inertia of the same area about the y-axis is Iy. Okay, moment of inertia of the area A about the y-axis is written as Iy. Then mathematically speaking, Ix is going to be given as area integral y square dA, and Iy is the area integral x square dA. Okay, the important point is this is an area integral or a double integral. Okay, this is an area integral, it's a double integral. Likewise, that's also an area integral here. Okay, so this is the mathematical definition of the area moment of inertia about a certain direction. Okay, or about a certain axis. All right, and so once we have this idea done, then all we have to do is we will start looking at this from the perspective of certain problems, certain shapes. And as we saw in the idea of centroids, right, we were mostly looking at composite shapes, and that is our interest here as well. And what I'm trying to do is I just draw like a nice box around these, okay, just so that we have this written properly. This is an area integral, just want to specify that here, okay. Area integral A, okay, and as we said, our aim is for composite bodies, but we will first do this for a very simple shape, which is an rectangle, and then I will introduce you to this concept of the parallel axis theorem, and then we will move on to solving some problems. Okay, one key idea that I want to state, or one key statement that I want to make here, is that the concept of the moment of inertia and centroids is very, very useful, especially when we come to looking at states of stress on a body. So the real need or the reason for moments of inertia will become more evident when we look at stress analysis in strength of materials. Okay, so I just want to make a quick note. Okay, so note the real aim, the need for defining moment of inertia and centroids will become more evident when we look at concepts of stress analysis in strength of materials. Okay, which is ME 2020. Okay, so the need for defining moment of inertia and centroids, of course, will become more evident when we look at the concept of stress analysis. Okay, that's typically what you'll be seeing in ME 2020. Okay, as I said, I'll be teaching one of the sections of ME 2020 next semester, so I'll be more than happy to expound on this particular idea next time we look at this in greater detail. All right, and now I come to stating one more thing, which is called as a parallel axis theorem, which is once again a very useful idea which will enable us to understand how to find moments of inertia for composite bodies. Okay, so I'm going to talk about the parallel axis theorem. Once again, no proof offered. Okay, parallel axis theorem. Okay, once again, no proof offered. Okay, I'll be showing the proof in my lecture notes. Okay, so will not be proved here. Okay, but the basic idea is this: if I know the moment of inertia of a certain cross section about its centroidal axis, then I can make use of the parallel axis theorem to find the moment of inertia about any set of axes parallel to the centroidal axis. Okay, so what is the aim? The aim or the reason is the following. If we know or can calculate the moment of inertia of a shape about its centroidal axis, okay, about its centroidal axis, then by using the parallel axis theorem, we can obtain the moment of inertia of the same shape about any set of axes that are parallel to the centroidal axis. Okay, the centroidal axis. Okay, this is the main reason for this particular theorem here. Once again, I want to underline certain things. So if we know the moment of inertia about the centroidal axis, then by using the parallel axis theorem, we can obtain the moment of inertia of the same shape about any set of axes that are parallel to the centroidal axis. Okay, this is the aim of the parallel axis theorem, and the basic idea is fairly straightforward, and I'll just first write the theorem, then we will exercise this on a very simple geometric shape, which is the rectangular shape. Using that concept, we will then move on to looking at moments of inertia of composite shapes, which is the main theme here, because composite shapes are what we are going to be seeing when we do stress analysis in ME 2020 in mechanics of materials. Okay, all right. So the theorem is given as the following. Okay, so I have a set of axes which I'm going to call as x and y first. Okay, this is the y-axis. Okay, and then let's say that this is the x-axis. Okay, then I have an arbitrary shape. Let's say that this is an arbitrary shape. Okay, and then let's say that the centroid of this arbitrary shape is sitting here. Okay, this is the centroid C of the arbitrary shape. Okay, and let's say that I have a pair of centroidal axes, which I'm going to label as x bar and then y bar. And then I see that one of my labels here has vanished into thin air. I need to maybe write that again. So this is the y-axis. Okay, then I have a set of centroidal axes which I have drawn here. These axes are going to be called as x bar and then y bar. Okay, this is an arbitrary body of area A, arbitrary shape. Of area capital A. Okay, C is the location of the centroid. Let us assume that this is something that we know. Okay, so x bar, y bar are the centroidal axes. So C is the centroid of the arbitrary area. Okay, then we will say that x bar and y bar are the centroidal axes for the arbitrary area A. Okay, let us assume that we know the moment of inertia about x bar and y bar. Okay, so let us assume that we can obtain the moment of inertia about x bar and y bar axes from the mathematical equations defined earlier. Okay, from mathematical equations defined earlier, the area integral equations. Okay, then we say that look at the figure. X and y are axes that are parallel to the centroidal axis. Okay, and I'm just going to copy this figure again so that I bring it down. Okay, so this I'm going to copy, and then I'm going to bring it down here. Okay, and I'm going to make a statement where we say that okay, the axes x and y here, x and y are axes that are parallel to the centroidal axes x bar and y bar. Okay, and let us assume we know the distance between xy axis and the x bar y bar axis. Okay, so these are all the things that we know. Okay, let's say that that distance is given to me by the following value. So let's say that this distance here between the x-axis and the x bar axis is going to be called as dy. Okay, and this is d subscript y. Okay, I just want to make sure that this is d subscript y, and then the distance between the y and the y bar axis is a distance d subscript x. Okay, so this is d subscript x. Okay, so in the following figure we see that dy and dx dy, okay, subscript y, I just want to write that out. Dy is the distance between x and x bar, okay, and then likewise dx, which is the same thing, subscript x, is the distance between y and y bar. Okay, let us assume that this is known to us. Then here is the following idea. Ix, which is the moment of inertia about the x-axis, is going to be Ix bar, okay, plus area of that arbitrary shape times d times y square. Okay, then Iy is Iy bar plus area times dx square. This is the parallel axis theorem. Okay, this is the parallel axis theorem, and once again here Ix bar and Iy bar are moments of inertia about the centroidal axis. So let me write that out here. Ix bar and Iy bar are moments of inertia about the centroidal axis. Okay, this is to be written a little more clearly. So Iy bar are moments of inertia about the centroidal axis, which is x bar and y bar, and then Ix and Iy are the moments of inertia about a set of axes parallel to the centroidal axis, and the distances dx and dy are the distances between the two parallel axes. Okay, the distances dx, dy are the distances between the axes xy and x bar, y bar. Okay, and of course A is the area of cross section of that arbitrary body, and this is the parallel axis theorem. This is a foundational thing. This is something you have to remember. Okay, so I just want to make a note here, so please remember this. Okay, I guess sometimes I forget English. Please remember this. Okay, the parallel axis theorem. Okay, All right, and what we're going to do is we're going to make use of a very gentle application of the parallel axis theorem first to a very basic section, which is a rectangle. The rectangle is a foundational piece for us. Everything that we do in strength of materials comes from a rectangle. Okay, and of course you can also think of it a triangle as a foundational piece, triangle and a circle. These are your basic simple connected shapes, but we are going to be focusing only on the rectangular shapes. Okay, so that's also something make a note of. Okay, so note. We will be focusing mostly on rectangular simple connected shapes and composite shapes that are made up of two or more rectangular simple shapes. Okay, this is just for the sake of simplicity, but the same ideas can be extended to combinations of rectangles and triangles, or rectangles, squares, and rectangles, circles and triangles, and so on and so forth. Okay, all right. So we will start looking at a very simple problem first. Okay, so problem. Okay, obtain for a rectangle of base B and height h, the moment of inertia Ix bar, Iy bar, and Ix, Iy. Okay, this is moment of inertia about the centroidal axis. Okay, and this is moment of inertia about a set of axes parallel to the centroidal axis. Okay, about a set of axes parallel to centroidal axis. Okay, so all we have to do is we haven't been particularly specified as to what is the x and the y axis here. So we have the freedom to choose, and I'm going to choose an axis that has its origin at the lower corner of the rectangle as shown. Okay, so first of all, I'm going to draw the rectangular shape. Okay, so here is the rectangular shape. Okay, I'm not taking any chances today, and I'm just going to draw certain lines and then duplicate them. Alright, so here is a rectangular shape, and we are told that there is a pair of axes that are set up in the following manner. Okay, so here is the y-axis, I'm sorry. Okay, so I'm going to call this as the y-axis. I'm going to call this as the x-axis. This is the x-axis. Okay, then we have the centroid of the rectangle, which is right at its geometric center. So somewhere here is the centroid. Okay, and then I have a pair of axes at the centroid of the rectangle, so that I'm going to call as x bar and y bar. Okay, so this is the centroidal axis. So this is going to be y bar. This is going to be x bar. Okay, and the height of the rectangle is given to us as the following: height h. And I'm going to go through this problem a little quickly because there are some basic differentiations that are being done here. So this height is h, and then the base distance is going to be little b, as you can see. Okay. Alright, so this is the basic aim. Find out x bar, y bar, moments of inertia. Find out moment of inertia about the x and the y directions for this rectangular shape. Okay, and what I'm going to say is, okay, here is a rectangle. Let me just shade it out. Okay, so that we have the rectangular shape, as you can see here, and this is the centroid C of the rectangle, as you have seen marked here. Okay, my first step is this. I'm going to consider a very small area here, which I'm going to call as dA. Okay, I'm going to consider a very small area here. Okay, and then I'm going to shade that area. Okay, and that area is going to be dA, which can be given as dx times dy. Okay, this is some kind of an elemental area or an infinitesimal area. Okay, infinitesimal area. Okay, so in our problem, the infinitesimal area dA is dx times dy. Infinitesimal meaning small, area, which is dA, is going to be dx times dy, and then I'm going to make use of the definition of the moment of inertia about x bar and y bar. By definition, okay, I can say that I x bar is the area integral y square dA, right, which tells me that I x bar is going to be area integral is a double integral. dA is going to be dx times dy, so this is going to be y square dx times dy. The limits of integration, you can see that the centroid is at the middle of the rectangle, so which means that I'm going to be going from minus h by 2 to plus h by 2, minus b by 2 to plus b by 2. Okay, so this is going to be minus h by 2 to plus h by 2, and then minus b by 2 to plus b by 2. Okay, this is the integration. I'm going to skip through the integration because we know how to do these integrals, and if you do the integration, then you end up getting my x bar is going to be 1/12 bh cube. Okay, and then by definition, once again, I y bar is going to be the following. Okay, it's going to be integral area integral x square dA, which tells me that I y bar is equal to integral from minus h by 2 to plus h by 2, the limits do not change, and then minus b by 2 to plus b by 2 x square times dx times dy, which tells me that I y bar is going to be 1/12 h b cube. Okay, these are two fundamental things that we got to remember. Okay, so this is one thing, this is the other thing. Okay, then what we're going to do is we're going to go back to our figure here. Okay, and I'm going to redraw this figure once again, okay, very quickly. Okay, just so we know what we're talking about. So this is the y-axis, this is the x-axis. Okay, then I have the rectangular shape that was drawn. The previous figure. Okay, then I had the centroid of the rectangular piece sitting somewhere here. Okay, and then I had the axes y bar and then x bar, right? This was x bar, and then this character here, we would call it as y bar. And of course I realized there is something funky going on here. Okay, this is the y-axis in the black color. Then we have calculated I x bar and I y bar. This is the centroid C, as you can see here. But then we also know that the height from x bar to x is going to be a height of h by 2. So this distance is known to me now. Okay, this distance, which I'm going to call as d suffix y, is equal to h by 2. And then likewise, you see that this distance here, which is the distance between the y and the y bar axis, is d suffix x, which is equal to b by 2. Okay, now these are distances, so we will be showing them in dotted lines, right? And so what do we know so far? Okay, so from calculations, we know that I x bar is equal to 1/12 bh cube, I y bar is equal to 1/12 hb cube. Okay, let me write the order properly. hb cube. You can immediately see that the units of moments of inertia will be in units of distance to the power 4. I just want to make a quick note of that. Okay, so the units for moments of inertia is distance to the power 4. So this is either mm to the power 4, inch to the power 4, etc. Okay, that's what you can pretty much see from these two expressions that we have derived, and that should hold true for any moment of inertia calculation. Okay, so we know that. Then we also see that, from the figure, dy is h by 2. Okay, so from the figure, d suffix y is h by 2 and d suffix x is b by 2. D suffix y is the distance between x and x bar. This is the distance between y and y bar. And then we apply the parallel axis theorem. Okay, parallel axis theorem. We know that Ix is Ix bar plus area times dy square. Iy is Iy bar plus area times dx square. Of course, area A is base times height h, or area is b times h. Okay, that's a basic rectangular area, right? There is not much to think about it there, which means that if I do the substitutions, Ix is going to be 1/12 bh cube plus area bh times h by 2 square, or if we do the simplifications, this is 1/3 bh cube. And then likewise, Iy is 1/12 hb cube plus the area b times h multiplied by b by 2 square, or if you crunch these numbers, you'll end up getting 1/3 hb cube. Okay, this is the application of the parallel axis theorem to find the moment of inertia of a rectangle. Okay, so what are the things you need to remember? Okay, so things to remember are the following. Okay, so let me make a note. Okay, you need to remember the rectangular shape. Okay, remember that. Let me maybe change the color that is being used here. Okay, so remember that for a rectangle, base B, height h. Okay, remember that the moment of inertia about the centroidal axis for the rectangle for a rectangle is Ix bar is 1/12 bh cube, Iy bar is 1/12 hb cube. This is something to remember. And the third thing to remember is the parallel axis theorem. Okay, this is also a key thing to remember. Parallel axis theorem, moment of inertia about the centroidal axis for a rectangle, the parallel axis theorem. I'm just going to scoot over and then copy these two things. Okay, so here is the basic thing. Okay, this is Ix and Iy. This is about an axis that is parallel to the centroidal axis. Dx and dy are the distance between the two sets of axes. Okay, these are the three things that you want to remember. Okay, remember for a rectangle that the area is base times height. Okay, that's fairly straightforward. Everybody knows that from grade 3, right? Then moment of inertia about the centroidal axis for a rectangle. This is something that we have derived, but this is something that you want to keep an eye on, and you want to remember these. Okay, then we remember the parallel axis theorem. There's also something called as a perpendicular axis theorem, which I will not dwell too much on, but the basic idea is the following. Okay, we don't need to remember this. Okay, this is just a digression. Maybe I'll just write this down where I had written the parallel axis theorem somewhere here. Well, probably I'll just take this figure here. Okay, I'll just take this figure. Okay, I'll just copy that, and then I will just put that down here. And there is something called as the perpendicular axis theorem. Okay, you have the x-axis, y-axis. Then we can draw something called as the z-axis. So let me write this statement a little better. Okay, so the perpendicular axis theorem. Perpendicular axis theorem. Let's say that here is the z-axis that is coming out of the page. Okay, this is perpendicular to the x-axis and the y-axis. Okay, so this is perpendicular to the x-axis and the y-axis. Likewise, the x and the y-axis are perpendicular to each other, as you can see here. Okay, and then here is one more thing. Okay, so this is the z-axis. Then we can say the following. Okay, we can say that the perpendicular axis theorem says that IZ is going to be IX plus IY. Okay, and in this particular case, you can say that if IX is x squared dA and y squared dA, IY is x squared dA, then IZ is x squared plus y squared dA. So from a general point of view, general expression, not very important right now, but you'll be using this in dynamics pretty often later on. Okay, you can say that IZ is integral x square dA plus integral y square dA, or IZ is integral x square plus y square dA, which you can write as some integral r square dA, right? If you have the hypotenuse as x and y, r, the length of the sides are x and y. So if I just draw quickly something like this, then this is going to be x, y, and then r. Okay, this is going to be y, this is going to be x, this is going to be r. Okay, and then we are just making use of the hypotenuse, and in many textbooks, this will also be called as the polar moment of inertia. Okay, this is something that you will make use of when you study torsions of shafts in mechanics of materials. So this will be useful when looking at circular cross sections. In strength of materials. Okay. All right, so we're almost there to go into composite bodies. So I just want to make a quick statement. Okay, so this is the end of these theorems. Okay, one important statement that I want to make about composite bodies. Okay, so moment of inertia of a composite shape is equal to the sum of the moment of inertia of its simple connected shapes. Okay, is equal to the sum of the moment of inertia of its simple connected shapes. And this precludes the use of the parallel axis theorem. Okay, this employs the use of the parallel axis theorem. All right, and so making use of this basic idea, we're going to look at the calculation of moment of inertia of composite shapes. We're going to make use of problems that we have already seen from lecture 25, which is the T section and the L section, and then we're going to continue making use of those. Okay, so let us go ahead and solve for moments of inertia of composite shapes. Okay, so we will now look at moment of inertia of composite shapes. Okay, and in the previous lecture which was lecture 25, we had already computed the centroid of an L section and a T section. Okay, we are going to be making use of these. Okay, in the previous lecture 25, we had already computed the centroid location of an L section and a T section, so we're going to be making use of these results. I'm not going to be deriving them again. Okay, so we shall make use of results from lecture 25. Okay, and this implies that the first step in the calculation of moments of inertia is always to find the centroid of the composite shape. Okay, so the first step, let me also write that down. So the first step, this is an important step. Okay, so note the first step in computing the moment of inertia of a composite shape is to obtain the location of the centroid of the composite shape. Okay, this is always the first step. So first step in computing the moment of inertia of a composite shape is to obtain the location of the centroid of the composite shape, because without doing the centroid calculations you cannot proceed forward. All right, and so we will make use of results from lecture 25, and then so let us go ahead and start solving some problems. Okay, let me see if I have enough space here for one problem. I think I can start off a problem here. Okay, so let me start off. So problem: obtain the moments of inertia of the following cross section about its centroidal axis. Okay, so let me draw the T section first. Okay, and here is the T section from the previous lecture. I think it was mostly a symmetric T section. Okay, I hope this turns out to be symmetric as well when the way I draw it. All right, so here is the T section, and then we were given the following dimensions for this. This was 20 millimeters. This thickness was also 20 millimeters. Then the width of the top flange, okay, this was given to us as 100 millimeters. Okay, this was 100 millimeters, and the height of the middle portion, okay, this is 80 millimeters. Okay, this top portion is called as the flange. Okay, there is no particular name for the middle section, so we'll just leave it that way. All right, and what we have to do is the following, for this problem, and I think what I want to do is I want to outline the different steps that are involved in the problem. Okay, so what are the steps to take? Okay, so steps to take: one is locate the centroid of the composite shape. So locate the centroid of the composite shape. Okay, that's the first step. Then the second step, obviously you see that these things are made up of rectangular simple connected shapes, so the details that we have used for calculation of centroid still holds true here. Okay, then what you want to see is mark the centroid of each simple connected shape. Okay, mark the centroid, each simple connected shape, and obtain the distance of these centroids from the centroid of the composite shape. Obtain the distance of these centroids locations from the centroid of the composite shape. Okay, that's the second step. And then the third step is this: make use of the parallel axis theorem. Plus the fact that centroid of the composite shape, moment of inertia of the composite shape is equal to the sum of the moments of inertia of the simple connected shapes. Okay, but these have to be with respect to the axis that you're asked to compute this with respect to. In this case, it's the centroidal axis of the T section. Okay, all right, this is something that we have already done in lecture 25. Okay, this is from lecture 25. Okay, this I'm going to take these details from there. Okay, so first of all, here are my steps. So locate centroid of the composite shape. That's the first step. Okay, locate centroid of the composite shape. Then mark the centroid of each simple connected shape, and then obtain the distance of these centroid locations from the centroid of the composite shape. Then make use of the parallel axis theorem plus the fact that moment of inertia of the composite shape is the sum of the moment of inertias of the simple connected shapes. Okay, so these are the steps involved, and what I'm going to do is I'm going to take the T section, and then I'm going to start by marking the locations of the centroids of the simple shapes, then draw the centroidal axes, and so on and so forth. Okay, so let's take this piece here. This is I'm not going to redraw this piece again. Okay, I just want to copy this and bring that guy down here. Okay, so here is my shape. Let me get rid of some of these unwanted things, and I guess I have to use the eraser for this. That is okay. All right, now what I want to do is the following. First of all, I have to mark the centroid of each of the simple connected shapes. Okay, so here is the centroid of this shape, and I'm going to call this is the centroid of the other shape here. Okay, I'm going to call this as shape 1. Okay, this is going to be called as 1. Okay, and then this is going to be called as 2. Okay, so these are the things that I have here. Okay, then what I have to do is I also have to mark the centroid of the overall T section. So that's going to be somewhere here. This was calculated from the previous lecture. Okay, so what I'm going to do is this. Okay, here are my distances first of all. Okay, so starting from the top flange, I'm going to mark some distances. Okay, bear with me while I do that. Okay, so here is one distance, then here is one more distance. I guess I should be scooting that creature down. Okay, and then I'm going to have a third distance right here. Okay, so these are all distances, so I'm going to draw them in dotted lines. Okay, and from here this is a height which we're going to call as the following. Okay, I'll label that in a minute. Then I have one more here. Okay, and then here is my last height, which I'm going to have here. Okay, then what I'm going to do before I do any of these things, here is what I'm going to say. Okay, this is the center of the main composite section, so that's going to be the axis labeled as x bar and then y bar. Okay, that's going to be the center of the main body. Then I'm going to have the center of these smaller individual shapes. Okay, I'm going to have I'm sorry, it's going to be called as this is since this is shape 2, this is going to be called as x2 bar. Okay, then I'm going to have y2 bar, that's y2 bar. Okay, and maybe I don't want to do that here, so let me do the following. Let me just extend this so that this peaks up all the way here. Okay, then this is going to be called as y2 bar, and likewise I'm going to be having one for this body here as well. Okay, this is going to be called as x1 bar. Okay, and obviously if I draw something from here all the way up to there, and that's going to be called as y1 bar. Okay, then here is the distances that I have marked, which I'm going to start labeling now. Okay, this distance I'm going to call as a distance y1 bar. Okay, this is equal to a distance of 10 millimeters because the total width here is 20 millimeters, right? This was 20 mm. Then this distance here is going to be called as y bar, which is equal to 32.2 mm. This is obtained from the lecture 25. Okay, then this third distance here I'm going to be calling this as y2 bar, and you will see that since this height here is if I mark it off, okay, this height here is going to be 80 millimeters, so the total length of that is going to be 40 plus 20 or 60 millimeters. So this is 80 millimeters, so this is going to be 60 millimeters. Okay, and so from the perspective of labeling, here are my labels. Okay, so first of all, x bar and y bar is the centroidal axis for the entire composite shape. Okay, then I have x1 bar, y1 bar is the centroidal axis for shape 1, and then x bar 2, y2 bar is the centroidal axis for shape 2. Okay, and then we know this distance here, if I label this out, that thickness is going to be 20 millimeters, right? That's 20 millimeters, and then the width of this top flange is going to be 100 millimeters. We know this from before, so if I just mark that as well, just to have all my distances written down. Okay, this is going to be 100 millimeters. Then I'm going to have a couple more distances here. Okay, these distances which I'm going to label in let's say brown color are the following. You see, I have a distance between the x1 bar and the x bar axis, which I'm going to call as dy suffix 1. Okay, so this distance here is going to be called as dy 1. Okay, and then I'm going to have likewise one more distance between x bar and x2 bar. This I'm going to label as dy 2. Okay, so these are my distances. I know this is a little confusing, but I just want to make sure that we all have everything here. So I have shape 1, which is this top flange. Okay, this is the top flange, is shape 1. Okay, this is the top flange, and then shape 2 is the middle vertical section. Okay, this is the vertical piece. Okay, if I start looking at the base and the height and so on, and if I start collecting this information, I can say the following. Okay, so for shape 1, okay, let me copy this figure which I need, so that we have everything on the same page. Okay, so I'm just going to copy that and bring that down here, and perhaps try to reduce its size. Okay, so that's not working in my favor. This looks good to me. Okay, here is the situation as I have labeled. Okay, so I'm going to say, okay, for shape 1, what is the height h1? h1 is going to be 20 millimeters. b1 is going to be 100 millimeters. a1 is going to be 100 times 20 millimeters square. Then dy1 is going to be what? It's going to be the difference between y bar and y1 bar. Okay, this is y bar minus y1 bar. Okay, and of course the first thing is I have to say that, okay, y bar is going to be 32.2 millimeters. Okay, this was obtained from lecture 25. Okay, and dy1 is y bar minus y1 bar, so that's 32.2 minus 10 millimeters, and I just want to write y1 bar here as well. y1 bar is going to be 10 millimeters, and this is going to be 32 minus 10, and so we can just leave it that way, 32.2 minus 10 Okay, this is for shape 1. Then for shape 2, I want to say that h2 is going to be the height, so that's going to be 80 millimeters, right? And then b2 is going to be 20 millimeters. a2 is going to be 80 times 20 millimeters square. Then dy2, look at dy2. dy2 is the distance between y2 bar and y bar. Okay, so that's going to be y2 bar minus y bar, and y2 bar, as you know, is labeled as 60 millimeters, so that's going to be 60 minus 32.2, so many millimeters. And I want to make a note here that the axes y bar, y1 bar and y2 bar are all coincident. You can see that they are all along the same straight line. Okay, so the axes y bar, y1 bar, y2 bar are all coincident. Okay, I just want to rewrite that. Coincident, which means that dx1 is equal to 0, dx2 is equal to 0 millimeters, where dx1 is the distance between y1 bar and y bar axes. dx2 is the distance between y2 bar and y bar axis. Okay, so which means that I can say that here dx1 is equal to 0 millimeters, and then dx2 is equal to 0 millimeters. And so I have all my information which has been collected. I have y bar from lecture 25, then I have h1 b1 a1 dy1 y1 bar, and likewise dx1, and so on and so forth for both these shapes. Okay, my aim is to calculate ix bar and iy bar. Okay, so aim is to obtain ix bar and iy bar, which is the moment of inertia about the centroidal axis of the composite shape. Okay, and here is what we're going to be saying. Okay, so ix bar is equal to the following. We said that moment of inertia of a composite body is the sum of the moment of inertia of the simple shapes, right? So which means that ix bar is going to be ix bar of shape 1 plus ix bar of shape 2. But you see that if I'm trying to find the moment of inertia of the shape 1, the top flange, about the x bar axis, there is a certain distance that separates the centroidal axis of the first shape from the main centroidal axis, which means I have to use the parallel axis theorem. Okay, all right, so we say the following then. Okay, then this is equal to ix bar is equal to ix1 bar plus a1 dy1 square, and then ix2 bar plus a2 dy2 square. Okay, this is the moment of inertia about its centroidal axis for shape 1 plus the parallel axis theorem that is used, and likewise for shape 2. Okay, this is for shape 1, this is for shape 2, and then I just start filling in the blanks. Okay, so this implies that ix bar is going to be 1 by 12 b1 h1 cube, and then a1 times dy1 square plus 1 by 12 b2 h2 cube a2 times dy2 square. Okay, substitute for things from the above. Okay, substitute for h1 b1 h2 b2 a2 a1 dy1 dy2 from above. Okay, and I get the following. Okay, so ix bar, after I crunch all the numbers, and I'm going to show this in much greater detail in the notes that I'll be posting. So ix bar, after the numbers have been calculated and substituted, where you see these are the numbers. Okay, h1 b1 a1 dy1 y1 bar, and likewise for the other ones, I end up getting the following. Okay, so ix bar is going to be 12.53 times 10 to the power 6 mm to the power 4, and likewise iy bar is going to be iy bar of the first shape, iy bar of the second shape. Okay, which is going to be the following. Okay, iy1 bar a1 dx1 square for the first shape, iy2 bar a2 times dx2 square for the second shape. And if I start filling in the details, iy bar is going to be 1 by 12 h1 b1 cube a1 dx1 square, 1 by 12 h2 b2 cube a2 dx2 square. Okay, And you see that we can make use of the formula 1 by 12 h1 b1 cube or b1 h1 cube, because we know that this is a rectangle and we have already derived the moment of inertia for a rectangular shape earlier in the lecture. Okay, so if I do the substitutions, okay, substitute for h1 b1 and so on, h1 b1 h2 b2 a1 a2 dx1 dx2 etc. from above. Okay, and then you'll end up getting Iy bar is 2.31 times 10 to the power 6 mm to the power 4. Okay, so this is the typical calculation. This is first of all saying that moment of inertia about the centroidal axis of the composite body is moment of inertia of the first simple shape about the centroidal axis of the main body, second simple shape about the centroidal axis of the main body, then use the parallel axis theorem for each shape, and then do the additions as shown here. Okay, and this is the same thing that we had used for Ix bar as well. And with your silent permission, I'm going to solve one more problem, pretty quickly. This is the L section that we had obtained from the previous lecture as well. Okay, so thank you for your patience, of course. Okay, I know that it takes a little time. So problem. Okay, obtain moments of inertia for the L section about its centroidal axis. Okay, and look at lecture 25 for the centroidal axis of the L section. Okay, I'm going to skip that calculation. Okay, so I'm going to draw the L section first. Okay, so here is the L section. Let's do that here. Okay, and what I'm going to do is I'm going to make use of what we have already done in the previous lecture and say that, okay, I have broken this into two pieces. Okay, so here is the first piece, and then here is the second piece, and then we have the dimensions that are given to us, okay, as shown here, and I'm going to call this as piece 2. Okay, and then this was piece 1. Okay, and the dimensions are as follows. So this was 20 mm in thickness, and then this thickness here was also 20 mm. Okay, and this height here was 100 millimeters from the top to the bottom, or this piece is going to be 80 millimeters from here to there. Okay, apologies. So what I found out is if I do it slowly, then I don't get those dotted lines, those pesky dotted lines. Okay, and then the dimension from here to here is 100 millimeters. Okay, and that I'm going to say is 100 millimeters. Okay, so the first step, as always, is to locate the centroid of each of these little pieces, and then the centroid of the main piece, and then go about our way. Okay, so the procedure is the same as the above. I'm just going to copy this figure and then get on my way. Okay, all right, so I'm going to start off by looking at the main figure. So I just want to create some space for it so that I have all these axes that I can label. Okay, so here is the first piece in the L shape. Then I'm going to have the second piece. You can break it into whichever way you want. Okay, either this way or the other way that I showed you in lecture 25. Both of them are going to be the same thing. Okay, so first things first, I'm going to have the centroid of this piece, which is going to be here. Okay, then I'm going to have the centroid of this piece, which is going to be somewhere here. Okay, then I'm going to have the centroid of the main piece itself, okay, which is going to be somewhere here, let's say, which we calculated from the previous lecture. Okay, and let me mark that here as well, and let me show that to you that in the previous lecture this distance was calculated as the following. So this distance from here to there was 32.2 millimeters, and millimeters, and this height was also 32.2 millimeters. Okay, this is the centroid C, 32.2 millimeters. This was calculated from lecture 25. All right, so we are on our way. Okay, so what I'm going to do is this. I'm going to first start off by drawing the centroidal axis for the composite body. This is going to be x bar, right? And then this height here is going to be y bar. Then I'm going to have the centroidal axis for the other two pieces, right? I'm going to have an x1 bar and a y1 bar. Okay, so this is going to be an x1 bar. Okay, here is x1 bar, and I'm going to have a y1 bar. Okay, here is y1 bar. Likewise, I'm going to have an x2 bar, and a y2 bar. Okay, so this is, of course, they're all straight lines, pardon me for that. Okay, these are this is the centroid C for the main body. This is the centroid C1. Okay, this is the centroid C2 for the second shape. This is shape 1. Okay, and then this is shape 2. Okay, and then we have all the distances that I can mark. Okay, so let me do that. So here is 1, then I have one more distance from here to there. Yes, then I have this distance that I know from here all the way to there. From here, I guess the center of that piece all the way. I guess let me take this C1 and take that creature and put it somewhere else so that I can write the distances. Okay, so this is C1, as you can see, centroid, and then I have the height from here, yes, all the way to here. Okay, and then this is shape 1, so let me do that here. That's piece 1. Okay, so here are my heights, so I'm going to draw that out. So first one is right here. That's this guy here. I'm going to call that as y1 bar. Then I'm going to have y2 bar all the way from here to there. Okay, and then I'm going to have y bar all the way from here to the bottom. I'm going to expand this guy. Maybe I'm going to take that and draw that here so that I can scoot that out, and likewise I can do that here as well. Okay, this is going to be this is going to be y2 bar. This is actually y bar. Okay, and this is going to be y2 bar. Okay, so I have all these distances done. Then likewise I'm going to have these following distances here. I'm going to have, starting from here, which is the origin that we had chosen yesterday, all the way to here is 1. Okay, then I'm going to have 1 from here to there. Okay, let me scoot this guy and bring it here. All right, almost there. This distance is going to be x bar for me. Okay, then I'm going to take this guy, bring it down a little bit, and do the same thing for this creature here, and then that is going to be x1 bar. Okay, as you can see, and then I'm going to have an x2 bar as well, which I'm going to sneak up on right here. Okay, so that's going to be x2 bar right there. That's going to be x2 bar. And of course I think it's a good idea to maybe shade these pieces so that you know what I'm talking about. Okay, and then I have the blue piece as well here. Okay, just to make the figure more cluttered. Fantastic. All right, and then what else do we have to do here? We have to mark out the distances between the different parallel axes, right? And here are the distances. So first of all, you see that I can take this x bar axis and then extend that creature. Okay, if I take that, maybe before I do that, let me mark the x bar right up here. Okay, this is x bar. I'm going to take this axis and extend that a little more. Okay, so that you can see the distances that I'm going to mark now. Okay, this height here is going to be the height from x bar to x2 bar, so that's going to be dy2. Then this height is going to be dy1. Okay, then likewise I'm going to have a distance between y bar and y1 bar, right? And that I'm going to mark as dx1. Okay, and then I have a distance between y bar and y2 bar, which I'm going to mark here. Okay, in a minute I'm going to take this guy and expand it here, and this distance is going to be, well, I had marked those in this color here, that's going to be dx2. Okay, those are my key distances, so I just want to mark them out. Okay, so this is a key distance here, that's a key distance, that's a key distance, and then that's a key distance as well. Okay, these are the four things, and then I'm going to start collecting all this information. Okay, so for shape, first of all, I had x bar as 32.2 mm, y bar as 32.2 mm. Okay, then for the first shape, I'm going to have h1. Okay, the height for the first shape is going to be 20 millimeters. B1 is going to be 100 millimeters. Then A1 is going to be 20 times 100 millimeters square. Then watch this, dy1, distance between x bar and x1 bar, is going to be y bar minus y1 bar. Okay, then that distance is 60 minus 32.2. I guess right, I'm sorry, that distance is slightly off. This is going to be 32.2 minus 10. Okay, so that's going to be 32.2 minus 10. Okay, so many millimeters. And then dx1 is going to be the following distance. You see, I have x bar and then I have x1 bar, so dx1 is going to be x1 bar minus x bar. Okay, so that's going to be x1 bar minus x bar. Okay, and x1 bar is going to be 50 and then 32.2, so many millimeters. And likewise I'm going to have the same thing for piece 2. Okay, for the second piece I'm going to have h2, the height is going to be 80 millimeters. b2 is going to be the width, which is going to be 20 millimeters, and then a2 is going to be 80 times 20 millimeters square. Then dy2 and dx2, look at dy2, right? dy2 is sitting right here between x2 bar and x, so that's going to be y2 bar minus y bar. Okay, dy2 is going to be y2 bar minus y bar. Okay, y2 bar minus y bar is going to be 60 minus 32.2 mm. And then likewise I'm going to have dx2, which is the distance between y2 and y bar 2. Okay, and so y bar and y2 bar, and that's going to be x bar minus x2 bar. Okay, and that's going to be 32.2 minus 10 millimeters. Okay, so all these have been collected together, and likewise I had that for the first shape as well. And then this was information from lecture 25, and all I have to do is apply the formula. If I have 3 shapes, I have the formula added 3 times. If I have 2, I do it 2 times. Okay, so I'm just going to write the formula here, and then we will leave it with the calculations as such. Okay, so here is the basic idea. So if I look at I x bar is going to be I x bar of shape 1 plus I x bar of shape 2. Okay, and so if I employ the formula, this is Ix bar is going to be Ix1 bar plus A1 dy1 square for shape 1 plus Ix2 bar A2 dy2 square for shape 2. Okay, and if I do the substitutions, Ix bar is going to be 1/12 b1 h1 cube plus a1 times dy1 square 1/12 b2 h2 cube plus a2 times dy2 square, and substitute from above. Okay, substitute for all quantities from here, okay, from above. And you may want to check my answer. I get my answer to be, I think this could be slightly off, but this is something that I want you to go and see. Okay, this is 3.9 times 10 to the power 6 mm to the power 4, and I would say check this for error. Okay, I did this number calculation very quickly, so it might end up having error, so I just want to check that, and I will, if I find an error, I'll point it out to you. Okay, then Iy bar likewise is going to be the following. Iy bar is going to be Iy bar for the first shape, Iy bar for the second shape, which is going to be Iy1 bar a1 dx1 square, parallel axis theorem, Iy2 bar a2 times dx2 square. Or if I do the substitutions, Iy bar is going to be 1/12 h1 b1 cube a1 times dx1 square 1/12 h2 b2 cube a2 dx2 square. Substitute from above. Above numbers. Okay, let me write this out in my hurry to finish the lecture. We have already taken up enough of your time. Okay, and here also you may want to check my answer. I get around 21.5 times 10 to the power 6 mm to the power 4. Okay, check for errors. Okay, this is something that I want you to do, but the basic idea remains the same. What you want to do is you want to first of all find out the location of the centroid. Okay, this is something that you found out from the previous lecture. Once you find the location of the centroid, then you draw the figure, you mark the centroids of the individual simple shapes, you mark the centroid of the main shape as well, and then start looking at all the distances. This is the origin that you had chosen. Okay, this was the origin that you had chosen, and then in the previous problem also, you had the origin chosen as that there, right? That was the origin. This was something that I had to mention earlier, right? This was the origin chosen previously. The O was the origin chosen during lecture 25. Okay, I will make a note of that here as well. Okay, O, which is this point here, O. Okay, and that is also O. So O is the origin chosen from lecture 25. Okay, that is important. I mean, you need to know what the origin is. Okay, we had this drawn here too, so maybe I'll make a small note of that. Okay, O is the origin that was chosen from the previous lecture. Okay, and likewise here as well. Okay, O is the origin that was chosen from the previous lecture. Okay, so once you choose the origin, you have all the distances written down. Then you say that, okay, moment of inertia of the composite body is the sum of the moment of inertia of the simple connected shapes. Then you make use of the parallel axis theorem. You look at all the distances, and then it's a method of crunching these numbers and substituting and solving. There is not much to these problems. They're geometric problems, but practice is important. I think many times these might end up having errors because the numbers are to be plugged in many times, right? So be careful with these problems. All right, so I'll call it quits for this lecture. I will be posting a review session on Carmen where I'll be solving a couple of problems and posting it online, the same way that we've been doing the lectures, and I look forward to that being as our last sign-off point. I hope all of you are doing well, and staying safe. Stay healthy. Practice these problems. If you have any questions, please get in touch with me. All right. Thank you very much. Take care of yourselves.